Morning, guys. Hello again. I think this is all good. Looks like we got about 5 seconds of lag today, so that's a bit better. Cool. So we're going to be resuming the normal distribution where we left off yesterday. Cool. Right, we're going to start by talking about the calculator. So, today's topic is the standard normal distribution or the standardized normal distribution. And I'm surprised that no one actually spotted this in previous lectures. So if we go to distribution, let's go to normal distribution, and we will plot anything really. Whatever this was left over from yesterday. So I don't know if you guys actually spotted that. The one I typed in has a mean of 20 and a standard deviation of 3. So if we go back down and draw it, yes, all right. So what I want you guys to quickly do then, looking at what they've sketched, what is the mean and what is the standard deviation of the normal distribution? There it is in the calculator. So have a quick, if you are with other students, have a quick chat. If not, have a look to see if you guys can read off the mean and the standard deviation from this normal distribution, and we'll see what you guys come up with. Nothing so far. Anybody? Mean and standard deviation of this distribution? Mean 0? Yes, you can clearly see that. How about standard deviation? Hello, Will. Welcome to the lesson. Standard deviation is not that clear from this graph, to be honest. The point of inflection is not very clear. Anyway, yeah, we'll have a look then. So, even though I told it to plot something with a mean of whatever it was, 3 and standard deviation of 2, hey Casper, we actually have this graph in front of us with a mean of 0. And this actually has a standard deviation of 1, which you can kind of tell that it's suggesting that the point of inflection is here. You can kind of see that from curvature as it goes from convex to concave. Yeah, kind of. But yeah, you have to believe me. This has a mean of 0 and standard deviation of 1. So what this is it's the standardized normal distribution. So it hasn't actually plotted what I told it to. It hasn't plotted a graph with a mean of 20 and a sigma of 3. It's plotted this thing instead. So basically, long ago, before graphical calculators were around, there was no such thing as just being able to solve any normal distribution. There was one normal distribution, which was called the standard normal distribution. And the standard normal distribution, we always said, was Z is a normal distribution with a mean of 0 and a standard deviation of 1. And that's like the official normal distribution, the 100% official OG normal distribution. So it's where it all came from. It's the one that started it all. And it has a mean of 0 and the standard dev is 1. So anytime that we solve a question, the calculator actually turns our question into a transformation of this original normal distribution. So when we're solving things x, n, mu, and sigma, the calculator is transforming this one into this one. It's then sketching this one, solving this one, and then turning your answers back into this one. It is a bit confusing at first because I think you guys have gotten used to just using the x ones. But anyway, so the way it does that, and if I draw, let's make some space here. If I draw both of these again, So we've got Z is n naught 1 squared, X and U and sigma. So the one on the right hand side, this one, this is what we've been using to describe our populations. So we've had a population of, I don't know, whatever it was, could be giraffes or something. We've got a mean of mu and a standard deviation of sigma. We're then trying to turn this distribution into the classic original normal distribution so that we can do our statistics on it, and then we're transforming it back into giraffes or whatever it was. The way it does that then, if I draw each of these normal distributions, again, I could put in mu plus sigma, mu minus sigma, and this one would be 1 and minus 1. The way it does that, and if we can kind of think about this as being a graphical transformation, we want to take this one. First thing we need to do is fit mu to 0. So we're going to try and transform this value back to 0. And the way we do that is we're going to take away the mean from every data point in our collection. So every data point in our sample or in our population, if we subtract mu, we're going to force the distribution to have a new mean of 0. So the first thing we do, Z equals X take mu. So we've done the first bit. Our data now has a mean of 0. All we need to do now is force our data to have a spread of 1 as opposed to sigma. So think about spread. Spread is how kind of spread out how wide your data is. Our data has a width of mu. We want it to have a width of 1. So we're going to squash our data using a scale factor of 1 over sigma. We're going to divide all our data by sigma to force it to get compacted in to have a standard deviation of 1. So we get this equation, and this is the equation that changes a X distribution into a classic normal distribution. And this is what your calculator does every single time it solves one of these questions. And back before we had decent calculators, students had to rifle through all these pages in the exam to find a massive table with all of the normal distribution calculations in it. Actually, I might give me a second. I think I have one under my desk. I'll be right back. Yeah, done that. So this is the old statistics textbook. And if I go right to the end, there's this big chungus table. Can you guys see this? And this has all your Z's in it and your probabilities in it. So instead of using the calculator and doing things really quickly, students had to rifle through this table in the exam to find out their calculations. And it was a nightmare. So you guys can be glad that you don't have to do that anymore. But yeah, so we're using this equation to change any distribution into a classic normal distribution. So let's just put some labels on this. So this is the Z value in standard normal. Oh, there's not enough room on the screen today. I'll need to fix that. So that says Z value in standard normal. I have written slightly off the screen there. This one is your X value so X's value in your distribution. Mu is the mean of your X distribution. And sigma is the standard dev in your X distribution. Right, is everybody okay with that so far? I know that is kind of tricky at first. We're turning one of these into one of these with a load of transformations. Please comment if any of that doesn't make sense. As I said, the lag is only like 4 seconds today, so very quickly we can address any issues. So please comment throughout today's lecture if there's anything you want me to go over or reiterate. No, cool. I'm guessing you're fine with that then. Right. Before we move on, so I thought we'd just try this then, just to show you kind of what's going on. Maybe re-explain the mean bit, says Dan. We'll go for an example and see if you guys still have any questions afterwards. So I've got here's my classic normal distribution. So it has a mean of 0, standard deviation to the edges about 4. The reason we always label it to 4 is, remember yesterday we said, was it 99.7% of the data was within 3 sigma. Well, in this distribution, sigma is 1. So if we do this, we're going to 4 sigma, which will be pretty much 100% of the data. So only ever go up to 4 with a classic normal distribution. Anyway, we are going to transform this data, which is the length of giraffe necks. So let's put that in here. Length of giraffe necks. I actually Googled this yesterday, so it would be accurate data. So yeah, the length of giraffe necks, average of 2.2. So we'll say x is a normal with a mean of 2.2 and standard deviation 0.2. So in order to do these calculations, we need to turn the giraffe calculations into the classic normal distribution calculations. So I can put 0.2 in here as well. So that's going to be 2 if you take away 0.2, and that'll be 2.4. So I want to turn this distribution into this distribution. And the way I'm going to do that, I'm going to subtract 2.2 from every giraffe's neck length, and that's going to make the average neck length 0. And then I'm going to divide every giraffe neck length by 0.2, which will force it to have a spread of 1 instead of a spread of 0.2. So basically, if you think about transformations, move left by 2.2 and squash it by a factor 0.2. And that's where our equation comes from. We would get z equals x minus mu over sigma, which in this case specifically would be z equals x minus 2.2 divided by 0. There's still not enough room on this screen, sorry. There you go. Cool. All right, does anyone have any questions on that so far? We're going to use it in context in a second, but yeah, Dan gets it now. Good. Excellent. Everyone else get it now? I assume so. Just imagine we're moving a distribution around. And to be honest, all you really need to do is be able to use this anyway. Cool. All right, moving on. So we do have to have one table. We don't have to have the massive table I just showed you, but we do have this thing called the percentage points table, which is quite small on your screen. So I might see if I can enlarge this. Can I? Yes. And somebody can't spell percentage, it seems, as well. That's good. Let's tweak that. Percentage, good. All right. So this is our percentage points table. So a few key points about this. This is a table that gives you the Z value if you know the probability. It's the only table you guys need to use, and there's not much going on with it. So Z value, these are our values on the x-axis. So if I sketch one for you here, there's z. All these things here are z values. So if you know the probability, you can find the z value. But we need to kind of look closely at this. So let's have a read through this. The values z in the table are those with which the random value z, so the distribution there, exceeds with probability p. Okay? In algebra, it says the probability z is greater than z is phi minus z, which is p. So the bits you need to kind of pay attention to there is this is a table for greater thans. Okay? You don't need to memorize the table. No, it is given to you in the exam. You just need to remember it's there and be able to find it. It's just in the stats section of the formula booklet. Okay, so the key point on this table is it's the probability that z is greater than, I'm going to put a in, I think it makes it a bit clearer there, equals p. So in other words, if you know the probability that z is greater than a, so if you know this probability, you can look for it in this table and you can find the z value, which is this, that corresponds to that value. So for these questions where the probability is I always say it's like an easy number, 0.5, 0.4, 0.3, 0.2, 0.15, 1. 0.05, 0.025, 0.01, 0.005, 0.001, 0.00005. These are all kind of like not integers, but they are kind of nice multiples of point something something 5, point something something 1. They're kind of nice numbers. There's no weird stuff. These I would say are not nice numbers. They are weird. These are nice numbers that you can kind of, if you see a question that says the probability is this, you can be like, oh yeah, that's a nice number. Let's look in the table. So I would kind of judge it on that. If you've been told, especially if you've been told a greater than probability, that's a nice kind of, again, not a whole number, but a nice wholesome number, I'll say. These are wholesome numbers. We can then use it in this is a quicker way rather than reach for the calculator. We can use the table values instead. So if I label this, we can put this into your notes as well. Z is your variable. This bit is value in table. They call it Z, as you can see in the table. I call it A because the students do get confused if they got two Z's in the same brackets. So it's the same thing. You don't have to call it A, you call it X, you call it Z, call it whatever. But it's the value in table. And then probability is the probability. Be careful though, it is greater than only. Greater than only. So if you want to use it for less than, you've got to be a bit clever about it, and there's got to be some strategy involved. Okay, so we are going to try a question using this table. So if I clear some space, hopefully you guys have all got that copy down. I'm going to need to make the table a bit smaller to fit this in. Please comment if you can't see the table and I'll try and figure something out. So I might do if I put it maybe up here. Hopefully that fits. Is that on the screen? No, it's definitely not on the screen. How about there? Yes, the A in my little equation was a Z in the table. You could use Z if you prefer. I think students often get confused by having probability Z is greater than Z. They're like, what? So yeah. There we go. Cool. Right. So the question is, given I might type this. Yeah. Got them. given that probability Z is greater than A equals 0.4, find A. Part B, given that probability, go back to text please, probability Z is more than A equals 0.1. This is an O, 0.1. Find A. So could you guys try these two? Oh, there's some comments here. Okay. Is the A in the brackets Z in the table? Yes, you'd be given you're given the probability. You want to find the Z value, which I've labeled A because I was worried you guys would get confused, but it seems you're getting more confused because I've labeled A. Yeah, the probability Z is bigger than a variable, is 0.4. Use the table to find out the value of the variable. Yeah, so you're given P to look up A, and that's why P is a lot nicer number than A. These are all nice numbers. These are all going to be easy to work out. And you can see here we got some nice numbers as well. All right, could you guys try the first one? I think the first one should be pretty easy. I'll give you a minute to do that. If you could comment your A value in the chat, and if you want to try the second one, you can. I'll give you, I don't know, 2 minutes, should we say, for these, and we'll see what happens. So 2 minutes starting from now. Well done, Dan. You have found the first value quite quickly there. See if you can find the second one. Everyone else, make sure that you can get to that value as well. We'll go through these in about a minute, unless someone gets the answer, and then we'll hurry things up. Yeah, well done. Cool. So Dan, Kezia both smashed it there, got the answers pretty quickly, and the klaxon went off randomly. Did it? No, it went off when you guys got the answer. In other words, when I saw that you got the answer. So that was meant to happen. Cool. Let's go through these then. So first of all, probability is greater than A. So we're going to draw these. Again, you always want to draw all of these things. So we'll call this one A, this one B. So for A, quick drawing. Probability Z is greater than A is 0.4. So we need to think, well, where is 0.4 going to be? Is it on the right-hand side or is it on the left-hand side? So remember, the whole thing has a probability of 1. Half of it has a probability of 0.4. So probability we're greater than this value A is less than half. So that tells me that A must be on the right-hand side of the mean, and it tells me this probability here, 0.4, and here's A. So it's greater than, we're allowed to just go straight into using our table. So if we go to the table, look for 0.4, there it is, our answer is 0.253. So that's it, 0.2533. Cool. All right, everyone okay with that? Hopefully. Hey Ben, how are you doing? Right, we're going to look at the second one, part B. So we've got given P, oh, let's just draw it again. So given P Z is greater than A is 0.1. I think I've actually, yeah, this is fine. Cool. Part B, draw this. So again, greater than it, 0.1. A is going to be even further to the right, and our probability there is 0.1 now. So we're expecting a bigger value for A. If we look in our table, 0.1, there it is, 1.2816. Cool. All right. Good. I'm glad, Ben. So hopefully that was okay. Let's try something slightly harder. So we're going to stick with the same idea. Keep the table up here. If I've rubbed these off too quickly, just watch the video again later. So we're going to try part C, which is given probability of Z is greater than A equals 0.8. Find A. Could you guys try that one? Bit more difficult this time. I will. Let's just have a race. Give you a minute for this and see how we do. Make sure you sketch it. Sketch is going to be essential to this one. Sam, you are close, but you are not correct. Sorry. Anyone else got anywhere? Maybe I was a bit tight with timing on that one. So Sam was very, very close, but you would not get your full marks for that answer. And let's see why. So we're going to draw a sketch. And remember, the mean for one of these classic distributions is 0. So Sam, hopefully straight away you're like, I can see what I've done wrong. We got the probability Z is more than this value is 0.8. So therefore my value A must be to the left of 0. And we know that this area is 0.8. Now, you'll have noticed, hopefully, our table doesn't go up to 0.8. It goes from 0.5 downwards. So we only know the values from 0 and up. So how we do this is we remember, the normal distribution is completely symmetrical. We're expecting A to be a negative number, so I'm going to put a little arrow and say negative. There will be a corresponding value, the same as A, but that's positive. So if I draw this in a slightly different color, there will be a second A value, which is positive. Now, just to reiterate, this isn't the value that we want to find. This is the value we can use in order to find our value of A, which should be negative. So I know the value greater than fake A is 0.2. So I can look up that in the table, which is 0.2 here, which is what Sam said the answer was. And we get 0.8416, which is this value. This value here, 0.8416. So the value that we're looking for, blue A, the real A, the original A, is going to be the negative version of that number. So our answer, A, is going to be minus 0.84. 1.6. Hopefully that makes sense. So Sam, I think you found you had the right idea. You found 0.2. You looked in the table. You found the value, but you didn't sketch it maybe. So you didn't realize that that is not the same as the blue value of A. We need to make it negative because it's less than 0. All right. If you've got any questions on that, please comment because this is tricky at first. Once you get it, it's quite easy, but is a new thing. No, I'm going to assume you're good with that. I'll keep checking, but I'm assuming you're good. Right, so we're going to try one more of these, and then we'll have done all the different versions of it you can come across. So last one, given P Z is less than A equals 0.2, find A. So again, let's say 2 minutes on the clock and see if you guys can find it. Don't forget to sketch it. I have just realized an error in my my ability to set good questions. Hopefully you guys will as well, and you'll find the answer quite quickly. So I think I'm going to change this because I've got to teach this lesson again later, and I think 0.3 would be a more suitable challenge. Yeah, well done, Sam. You've spotted it. Cool. Yeah, so I set you the same question twice by mistake. I just asked it in 2 different ways. So we're going to go through this as an example, but using a different value. So just so you can see this version as well. Probability x is less than A is 0.3, so A is going to be here. This is going to be 0.3. Remember, the table only works for positive values of A, and it only works for probabilities on the right-hand side of the distribution. So we're going to say, well, we can find this A instead, which would be 0.522. So RA is going to be negative 0.5244. Cool. Hopefully that's all good with you guys. It's not hard. If you sketch it and you remember 2 things about the table, it's greater than only, and it only has positive Z values. It's only doing half of the whole distribution. And it's kind of a lazy thing. It wouldn't have been much harder for them to print the table twice, but they need you to do some kind of mathematics. Cool. Right, moving on then. So what's next? Cool. Right. So we're now going to try one that you guys can do on your calculators. I'd like you to just give these a go. They should be straightforward, just inputting stuff to the calculator. You can see we've got the A values. We want to find the probabilities. So 2 minutes for this. It's just a calculator activity. Cool. All right, I'm back. We don't always have to have the klaxon. It's a gimmick that sometimes we'll use. Um, yeah, cool. So these should have been pretty easy. I didn't actually write down. Someone left a mock paper. Yeah, cool. The first years are doing that. Don't worry about that. Cool. All right. So we can sketch these, I suppose. A nice quick sketch for each of these ones. Remember, it goes from 4 to -4. We've got 0 in the middle, so we're going from minus 0.85, so about here, to minus 2.16, about here. So that's the area we're looking for, should be less than 2.5. While I'm at it, let's sketch the other one. This one. Oh, interesting, it's the same kind of stuff. 0.85. Can you see that? Yeah. So 2.16. Yeah, so I think my point in this was, again, iterating that areas are going to be the same. So if I bring up the good old calculator, make it a bit smaller. So we've got a distribution, normal distribution, NCD, lower minus 2.16, upper minus 0.85. Yeah, I would always sketch it. Always sketch it, because you can type stuff in wrong to your calculator and you won't know unless you've got a sketch. You know both of these should be less than 0.5. Sigma 1, because it takes seconds, Sam. Don't be lazy. Draw it. Draw it as well, yeah. Always draw it. Be sure. So yeah, 0.1827. Or 1823. So there's two twos there. Go back, do the other one as well, just to show you guys it's the same thing. So we got this time 2.16. Oh wait, 0.85 is our lower. And 2.16. And there we go, same thing. Cool. So yeah, there's our answer to both of these, 0.1823. But yeah, always sketch them, please. The amount of time it takes is definitely worth doing. Okay, what's next? Moving on. Here we go. This is a good question. So, can you guys read it? Is my first question to you. If you can, let's give it a go. Can you see that? Is that big enough on your screens? I can make it bigger. I'm gonna assume you might want it slightly bigger. Cool. I'm hoping that's all right. Okay, could you guys give this one a go then? It's a bit more involved. Maybe 5 minutes for it, I guess. It shouldn't take too long though. But yeah, give it a go. Comment the answer when you've got it, and I'll set up a timer. 4 minutes. How about that? But again, I would sketch all of this. Oh, and the equation from earlier if you need it. Dan has got part A correct. Well done. See if you can do part B. Everyone else, make sure you can get part A sorted, and then try and move on to part B. I need to get some more sounds on my soundboard. That's the only one I have. Suggestions, yeah. If you guys can suggest me some good sounds for my soundboard, hit me up with some comments at the end. Nice. Yeah, well done, Dan. Cool. I will give the rest of you. I'm assuming that Dan's the only one that's done it. Dan's the first one to comment, but I will give the rest of you another 30 seconds just to try and get that done. Dan, you can put your feet up for 30 seconds. Enjoy. Cool. Right, let's give it a go. So back we go. Right. So yeah, we've part A is like we were just doing. We need to use the calculator to find z value. Part B, we're now transforming our z value back to the x value that fits with that. Cool. So quick sketch. Put it here. So we want to try and find the z value. For z greater than it is 0.025. So there's our z value, 0.025. So that's what we're trying to get. So if we look to the table, 0.0250 is here. So we get z is 1.196. I'm being an idiot. 1.96 is what it actually says. So there's the answer to part A. All right, part B. So looking at this then, a VitaJet program takes only the top 2.5% of candidates. So the top 0.025, so it's the same number. Given the scores are modeled using normal distribution with a mean of 80 and standard deviation of 4. So you've got x is normal, mean of 80, standard deviation of 4. Find the score necessary to get on the program. So we're basically coding the z value we just found back to x using the red equation up there. So we're going to get z 1.96 equals x, the thing we're trying to find, minus 80, which is mu, over sigma, which is 4. So you multiply by 4, add 80 back on, you end up with x equals 87.84, which has a score, I guess we could say it's 88% in the test maybe, so you might want to after that say 88 on the test. Because you can't get 87.4 on a test, and it does say marks, I think. Does it say percentages? It says score, so I think we should probably have an integer answer. So yeah, 88 does sound like a better choice. Cool. All right. Let's try another one. We're doing pretty well today, I think. We've got how much have I got left? We're about halfway through, and we're about halfway through. Good. Right, we're going to try one more of these, and that'll be enough practice on this standardized normal distribution. So we've got this question about light bulbs. It's smaller, but I think my table actually, the photo of the table looked a bit better. If you do want me to make it bigger, let me know, but you might be able to see that. Could you guys give this question a try? So once more, I will give you some time. That's a bit better. Cool. All right, yeah. Could you guys? So it's 4 marks worth this one. I will be kind and give you 5 whole minutes though. So yeah, there you go. Give it a go. I think we should ban Dan from answering first as well, maybe. So Dan, you can type your answer in the box, but you're not allowed to hit enter until someone else has got the right answer. So yeah, make sure you're sketching this. One sketch will do for all the information they've given you. And you need to work out what they mean by 10th to 90th percentile. So that's a nice bit of recap from last year. Isaac, what are you saying? Between Norton. How do you mean? How do you mean is it between those two? You might be able to do it that way. I mean, 1.2816 is a correct bit of it. Do a sketch, Isaac, if you haven't already. You've got some right numbers there, but you need to use those. Use those to do something else. I mean, yeah, it sounds like you found your Z values, or one of the Z values. Dan, you done already? Did you get? Go on, let's see what you got, Dan. I'm still going to give everyone else the rest of the time, but that was fast. I want to see what your answer was. Yep, that is part A bit. Give part B a go. Cool. Right, I'm going to put a sketch up for part A. So there's my sketch. So you're trying to find the two Z values corresponding to those two. And because it's symmetrical, if you find one of those values, the other one's going to be the same value, but negative. Right, you got 40 minutes, 40 seconds left. Go on, Dan. What do you get? You got 10 seconds to type your answer. What is the range? Yes, that is correct. So the range would be 100, 144. Yeah, I guess you could do that as well. Because it wants the range, you could literally just subtract the two, and that's the range of range values. But yeah, good, cool. All right, yeah, why not? Always. All right, so part B. So, oh wait, we haven't done part A yet. So looking in the table, we know greater than, which is this region here. If you look in the table, is 1.2816. So the other one is going to be minus 1.2816. Okay, what part B is asking us to do is to code these or uncode these two values and turn them from a classic Z distribution back to one that relates to light bulbs. So we're going to turn these back into light bulb numbers. So we know the light bulb thing is x is normal with a mean of 1175 and a standard deviation of 56. So that gives us the numbers we're going to use to code these. So we need to code each one of these separately. So we'll do this one, minus 1.2816 equals x minus mu. Mu is 1175 over 56. And the other one will have the positive version, 1.2816 equals x minus 1175 over 56. Cool. And all of that is using the z equals x minus mu over sigma. Cool. So we want to find the range to the nearest hour. So we're going to rearrange these two equations, multiply both by 56, and then add 1175. And for this one, we get a range, or we get a value of x is 1103.23. For the other one, we get 1246.77. If you subtract those from each other, round it up, we get the range is 144 hours to the nearest hour, which is what I wanted. Cool. All right. Anybody got any questions about this one? I will wait 10 seconds and see if there's any issues. Ugh. Doesn't look like it. Cool. Right, that's all the practice we're going to do on the standard normal distribution. It will be in the assignments. I do suggest you guys keep doing the assignments. You've got the answers, so please keep doing those. Can you give? Let's see. The range of life to the nearest hour for a standard bulb. I don't see why you couldn't. I think they wanted the actual just the range of what range it was, but I guess it's the same thing. I think you might be right with that. Yeah. So yeah, if you do need any more practice on these ones, page 49, questions 4 and question 6 would be some good practice in addition to this week's assignment. All right, so for the rest of the lecture, we've got about half an hour, which should be plenty for the last bit. We're now going to try and find mu. Find mu and sigma. Let me just sort this screen out. Finding mu and sigma. So far, we started off, we knew A, we knew the value, and we used it to work out the probability. Then we had the probability, and we used it to work out the Z value. But we haven't had to work out the standard deviation or the mean. So the way we do these, and it's kind of a mix of what we were just doing with the standard normal distribution, we can use our equation z equals x minus mu over sigma to find mu or sigma or both. So we're going to try one of these as an example, and then you guys are going to try a slightly harder one. So let's have a read through this. I'm told x is a normal distribution with a mean of 50 and an unknown sigma. Given the probability x is less than 46 is 0.2119, find sigma. Okay, so it sounds alright. We've got everything apart from the standard deviation. But we can't go straight to the calculator and type stuff in. It won't work. The calculator needs sigma to work. The only equation we know that involves sigma is the one I just got rid of, z equals x minus mu over sigma. And we do know a lot of these things, so I can go through and kind of fill in that equation. Z, we don't know, equals x. Well, x is 46 minus mu, well, mu is 50 over sigma. So now we've got two unknowns. We need sigma, we don't have z. So the question is, how could we find z? Because if we can find z, we can just put it there, rearrange this, and find sigma. So if we look back through what we've been told and what we've used 50, we put sigma in as blank, we've used 46, but we haven't used the probability. So the idea with these questions is we can use the probability to find z, which then we can uncode in order to find sigma. So if I do a quick sketch of this, because you always want to sketch these. If I draw, so our mean was 50, the value we've been given is 46, we've been told this area is 0.2119. I can find the z value, because obviously these are x values. I can find the z value that corresponds to this. So obviously the 0 is the mean. We can do that just using a calculator. Find z, put it into this one, and then we can find what sigma is. So if I bring up the calculator and squeeze it in here. What I need to type in then, my lower is going to be, well, we're talking about z now, so let's go for, I don't know, -6. -4 would probably do the job. Upper is the, oh, sorry, we need to do inverse, don't we? Because I don't know what z is, and that's the thing I'm trying to find. So tail is to the left, area is 0.2119, sigma is 1 because it's a standard normal distribution, mu is 0 because it's the standard normal distribution. Execute, and it tells me z is minus 0.998. So I can write that down, minus 0.99. Sorry, what am I talking about? Minus 0.7998. So I'm going to round that. Let's say z is minus 0.8 will do. That's pretty accurate there. So I can then take that z value we've just found. Let's get rid of the calculator. Put that back over here, and we can find sigma. So minus 0.8 equals 46. Take 50 over sigma. And if I rearrange and solve that, we're going to get sigma equals 5. Cool. Seem okay? So we're still using the standard distribution, still using z. And we're using z, well, we're using that distribution to find a value, to uncode it, to find sigma. And you could do this with the mean as well. It could be the same question, but they give you sigma, they gave you 5, and they want you to try and find 50. Exactly the same method. What you guys are going to do next is they're going to give you 2 facts. So rather than just tell you, like this question did, this bit here, they will give you 2 of these statements, and you will need to do this process twice and solve it simultaneously to try and find mu and sigma. Cool, right, I'll just see if there's any questions, and then, okay, do we ever use central tail? No, central tail, yeah, it's not very good, because really quickly then, for it to be a central tail, you need it to be the same on either side. How often are you going to get, I don't know, 0.1 minus 0.1? How often is it going to be symmetrical about 0? So in that case, I think you could use it. Otherwise, it's not much use. So if you tried central tail, yeah, it gives you the area, but it assumes that it's actually central. So I've never ever needed to use it. So probably not, no. Any other questions, guys? I guess not. Cool. All right, so I'm going to try this question. So it's nicely handwritten. I think I've given you all you need there. Let's say 5 minutes for this and see how you get on. If you're stuck where to start, I would do 2 sketches, one for each. Maybe you could fit it on one sketch. Yeah, you could probably fit it on one sketch. So you got greater than 35, less than 15, just to help you guys out a little bit. If the mean we don't know, I'll let you do a bit more. Try and think where 35 and 15 would be on the sketch based on their probabilities. Then find your z's, and then uncode to find mean and standard deviation. How do you know which side to put them on? Okay, have a think about. So the first one, x is greater than 35, is tiny. There is not much chance of being greater. The other one, there is, again, it's not a big probability. There is not much chance less than. You want to kind of logic your way through it, so I'm thinking about just the statements and the probabilities involved. Greater than 35, not. We will go through it soon anyway. Cool. Right. That is time. So, as I was just saying, 35 must be on because the chance of being bigger than 30 is tiny. 5% chance of being greater than 35 must be. And for the other one, 15 this side because there's a stand 15. Hopefully that explains it. Okay, so we need to find the z values that correspond to. Add our calculator, put in inverse, use our probability. So if I go back to 15 for left hand side, area point u is 1, or other way around, sigma is. And we get the Z value that corresponds to our 15. Part of it done. Same idea now. We're going to put the tail to the right. Remember, if you're on a class whiz, there's an extra step. You've got to do the 1 minus the probability because the class whiz only does less than. For this next one, this on the class, just type it. Class whiz, you so 9, 7. It'd still work, but you've got to have that extra step. Sound has gone bad. Ah, that's my. Is that better? Is that any better? Can you guys hear me? I tried faffing around with noise gates if I could fix the audio, so I shouldn't have done that. Sorry. Did you guys hear all of that? So we found Z. We found Z based on the standard normal distribution, and then I was just talking about class whiz. So to do this on the class whiz, you'd have to do 1 minus this 1 minus this probability to find all this bit, and then type that into the class whiz in order to find the Z value that corresponds to 35. Okay, that's cool. Yeah, it's probably the quieter words that I gated. So yeah, if you type all that into whichever calculator you use, and we get the Z value there is 1.96. Cool. All right. So now we're going to use those two bits in two simultaneous equations to find mu and sigma. So I'll keep the color coding. We're going to say minus 1.05 equals 15 take x, 15 take mu over sigma. And for the other one, 1.96 equals 35 take mu over sigma. So we can rearrange those two quite easily and get minus 1.05 sigma equals 15 take mu. I rearrange the other one to get 1.96 sigma is 35 take mu. And you can just solve those simultaneously. You could do it on the calculator feeling lazy, or you could subtract those if you wanted to and do it manually. So yeah, if we do the first, if we do this one, take away this one, we would get 3.01 equals 20, which, does that look right? Yeah, that does. So sigma comes out as 6.64, mu comes out as 21.98. Let's get out of the way. Cool. Yeah, you can solve it simultaneously however you like, but that's the method. So you take the two values you had, find the corresponding Z values. You can always find the Z values because we always know for Z, mean is 0, standard deviation is 1. So you can always find Z, and then we're just using these two equations to code or uncode them. Should be pretty straightforward. With practice, should be pretty easy. Have you guys got any questions about those? Ask me now, because you're about to do one on your own for real this time, and we'll see how you go. I didn't get those values. Oh, that's good. Which values, Dan? Which values didn't you get? The final values or the Z values? Let me check, because I did that pretty quickly. Can you go over simultaneous bit again, please? The final values. Okay, which bit? So from here. So let's work our way through this. So these two are fine, obviously. So I set these up, I times up by mu up to by sigma to get this equation, and times this one by sigma to get this equation. Then I saw this one was positive and this one had a bigger value here, so I did this thing, take away this thing. So 1.96 take minus 1.05. Basically, I'm adding these two numbers together, so we'll get 2.9. Well, that's going to increase that to 3.01 sigma. 35 take 15 is 20, and minus mu minus minus mu is 0. So I get to this equation, so I can divide 20 by 3.01 to get 6.64. And if I put 6.64 back into here, let me just check this. I think it's right though. 1.96 times 6.64, and then do 35, take answer, and I get 21.98. So yeah, those are right. Does that make sense to everybody? So subtracted this blue one from the red one. Blue take, or did blue take red, got green, solved green, put that back into one of these, and got mu. Down's a plonker. No, it's not. It's easy to muck up simple things. And it doesn't matter when you do, because simple things, whatever. Okay, so could you guys try, I'll just neaten this up for my next lecture. You guys are going to try the same thing on your own. I think it's an official version. I think it's one that I didn't make myself. Yes. Oh, look, there's all the answers. I guess I should get rid of those. I think. Is that what I meant to do? Yeah, well, there's the answers. We've got time, so let's get rid of this. There's a hint there as well, you can see. So, masses of penguins on an island are normally distributed, mean mu to sigma. So you straight away, you know, I'm going to have to find mu and sigma. Given 10% have a mass less than 18 and 5% have a mass greater than 30, sketch a diagram, find mu, find sigma. And then part C is a binomial question based on the probability you've done in part A and B. So, I've got rid of how many marks it's worth. It's probably a few. I will give you guys 5 minutes, and that should leave us just with enough time to go over this. Comment if you need help though while you're doing this. How are we getting on? Anyone need any help? Nicely done, Regan. See if you can get part C done in the next 40 seconds. Decent. Really well done. More time, please. Oh, go on then. Can I do that? Can I? I can just pause time. I'll come back. Hey. Uh, I'm gonna sketch it because I don't want to keep you guys past the end of the lecture, but you can keep working. I'm just gonna draw the sketch, which you should all have by now anyway. So, don't know what mu is. Put mu. 10% have a mass less than 18. There's 18. I might color these as well. Why not? And 5% have a mass greater than 30. There we go. So there's all my data in the diagram. Cool. Right, I'm gonna start working for it. Hopefully you guys are close to finishing now anyway. So on the calculator, we're gonna put 0.1 in as our probability. So tail is to the left, area 0.1, execute. And we get 418, the corresponding Z value is minus 1.28. Same thing with 30, so put our tail to the right, or if you're on the class wiz, do 1 minus 0.05, area 0.05. Execute 1.64. Cool, so those are my two values. Now we're going to do the whole finding mu and sigma. So 18 equals, no, wrong way around. Minus 1.28 equals 18 minus mu over sigma. And 1.64 equals 30 minus mu over sigma. And if you solve those simultaneously, I guess we could do this one. Yeah, go on then, we'll solve these simultaneously. So 1.64 sigma equals 30, take mu. And for this one, minus 1.28 sigma equals 18, take mu. So again, I'm going to take one of these from the other. I'm going to do this one, take this one. So when I subtract those, it's going to add my two things together. So we're going to get 2.92 sigma equals 30, take 18 is going to be 12. So sigma equals 4.101. Sub that back in and we get mu equals 23.26, which are hidden under the calculator. There you go. Cool. All right. So next up, we want to find the probability at least 4 of the penguins have a mass greater than 25. Cool. Right. We can't actually use anything we've done so far. It's a good thing we found the mean though. We need to use the mean and sigma. So sorry guys, if the lecture's gonna be over soon. If you didn't finish copying this, you can just skip back a couple minutes. So here's the bits that we need. Let's write them down. So we had penguin masses. I'm gonna say M. M was a normal with 23.26. It seems awfully light for a penguin, but I don't know. 4.101 squared. And we are then going to be solving on the other side a binomial. So x is a binomial. We've got 10 penguins and we don't know the probability. And we want to try and find the probability that x is greater or than or equal to 4. And the probability we need is the probability that their mass is greater than 25. So if all that makes sense, let's talk through this quickly. So here's my normal distribution. This is the penguin masses are distributed normally with a mean of this and a sigma of this. Part C wants us to find the probability more than 4 penguins have a mass of greater than 25. So to do this, we need to find the probability that they have a mass of greater than 25. And that's going to be written here. And the way we do that is with our normal distribution. So we want the probability M is greater than 25. So we can do that on our calculator, which I'll bring back now. So it's a standard normal distribution. We're trying to find the probability now. So NCD, lower is going to be 25, upper 1,000, that would be a heavy penguin. Sigma is 4.101, and mu is 23.26. Cool, draw it. Looks good to me. So our probability, P, is 0.3357. So that is the probability that I need to use in the binomial question over there. So we can fill that in. That's going to be 0.3357. And we're trying to find the probability x is greater than or equal to 4. So back to our calculator. Again, if you're using class Wiz, it's a little bit more difficult because you have to do the whole 1 minus thing for your binomial. So we go binomial, BCD, variable. So our lower value is 4. Upper value, well, there's 10 penguins, so upper value is going to be 10. Number of trials, there's 10 penguins, and the probability of success 0.3357. Cool. Execute, and we get our probability is 0.4472, which is actually slightly different than what I thought earlier, but I have tweaked everything very slightly there. So yeah, 0.4472. Dan, what's Dan saying? When emperor penguins fast, the breeding season, they weigh 23 kilograms. Ooh, so this is a fasting population of penguins in the breeding season. Cool. Interesting. I'm glad we've got that fact. Thank you. Thank you for that, Dan. I was going to check that because the answer did come out. Ah, no, it's just point 0.02 off, isn't it? So I